Hello again, welcome back to another coding session with Bangalang, our low-level explicit compiled procedural language that runs on the CPU and GPU but does not have break and continue. So in the same theme as last week, where last session, well, depending how often I release these, maybe it was last week, but in the last session we finally added unsigned integers, dubiously. Now we're finally going to add break and continue to loops. I'm guessing the viewers of this channel know what break and continue are. If you put in a for loop, break will exit the loop and continue will move to the next iteration of the loop. So I guess they're keywords. We need to give them nice colors. And you know what? I think I'm going to actually put them in tests. I think I'm actually going to make some tests. So we have all these if tests. Here's a for test. For expression scope. For expression scope. So let's say put it at the end of the for loop stuff. So for, I'm just going to call it for break and for continue. So here we're going to say if value equals, so we start at 10, we decrease every iteration, so let's say 5, then break, and this one I'm going to say continue, so maybe we should actually put it at the top. No, that's not going to work. We're just going to continue forever. So maybe it's better with these to do this. We could even do this, do like a regular one, and we're doing the sum. So when we get to 5, no, we still put it at the start. So when we get to 5, then we break. And here, when we get to 5, we continue. Sum plus equals value. Okay. So we don't need that there anymore. So we kind of need to work out what the result's going to be. So for this one, when we're breaking, it's going to be 10 plus 9, 8, 7, 6, but not plus 5 because that's when we break. So 10 plus 9 plus 8 plus 7 plus 6 is 40. So that one should be 40. And this one, if it's 5, we're going to skip 5. So that should be just 5 less, should be 50. Hopefully those tests work. So now let's implement it. Break and continue. So we need some new keywords, right? I feel like tokens. Yeah, here we have a list of keywords. So we're going to add break and continue. And I also want to add them to our Bangalang settings here so that they are nicely highlighted. Okay, so break and continue are now considered keywords. And I guess they are statements, aren't they? If we go to our grammar. Yeah, they're like whole statements. Huh. Didn't think about that before. So it's like return. It's like break, continue, return. So this one is break, continue, and they definitely don't have anything after. That's it. It's just break is break, continue is continue. That's it. Return can have an expression after it. Which is optional, actually. It depends on context. Sometimes it's required, sometimes it's, sometimes it has to be there, sometimes it has to not be there. But in terms of grammar, to keep it easy, I'm just going to call it optional. So break and continue are statements, so we need to add it to our statement list. Where did I put it? Before return. So break, continue, they are statements. Break, continue. Huh, wow. I wasn't expecting to add new statements, actually. Somehow I didn't realize that until just now. So when it comes to parsing, I guess when we come to statement, yeah, we already base it on keywords. So quite often they start with keywords. So I think these are in, no, these are not alphabetical order. I guess they're in the order that they show up in the grammar. If for return, so if for break, continue, return. Do I like this ordering, or should it be continue, break? You know, I'm so picky about this. I'm going to make it continue, break. Continue, break. For continue, break. Okay, so let's go back here. For continue, break. But we don't need like a whole thing here for parsing because it's so simple, I feel like. Continue. What was I looking at? Return. So it's like, we're just grabbing the token. But we're not actually using it. Right. So maybe I will. Okay, fine. I'll make separate files. I feel like it's a bit silly because they're so small. So we need a continue, which I guess needs an underscore. Just like that, basically. It's very simple. We don't need that context. So we need a new type. LMN continue underscore and break underscore. Cool. So break is going to be basically exactly the same, except we have break instead of continue. And it creates a break node. All right. So that's parse continue, pause, break, doesn't need context, like so. So that takes care of those. We do need, I think it's in the AST, no, not the U tool, probably in the types, statements. Like that. They are considered statements, so we add them to the statement list. So then anywhere where we're talking about statements, they should hopefully take care of it. So that's the parsing done. Now type checking of a statement. Let's continue, break. So basically the only thing we need to check is that we are in fact in a for loop. And how do we know that? At the moment, there's no way of knowing. Type checking context. Yeah, at the moment, there's no way of knowing. So I guess we need to add something. I feel like there's maybe a better way than doing this, but this, I mean, this should work. We'll just say, are we inside a for loop? You know, very simple. And then when we type check our for, oh yeah, we create our own context for the for. So this copy should copy within for. Is there anything else we need to do? No, I think that's it. And then, so here, for a for context, go within for equals true. Easy, because that for context is going to get thrown away at the end of this procedure, and we'll go back to that context, which is not within for. So I think that should be it. That should tell us whether we're within a for or not. Okay. See, the other way I was thinking was we could have something here that says kind of like, what's the scope? And the scope could, you know, it could either be like procedure or for or whatever it is, you know, like scope type or something. But maybe that's a bit overkill for now because the only one we care about is for. So I think that's that. We know whether we're in a for. So now when we type check continue, I think basically the only thing we care about is whether we're within a for. If we're not within a for, then we need to throw an error. Where's an example? Here we go. Like that. Yeah, so this is not return, this is continue. So then we could say continue must be within a for loop, something like that. Okay. technically right now, our fors, you know, they can have arbitrary statements in these places. I want to change that actually. I want to change it back to something more restrictive. So I'm not going to worry about, you know, because, and I mean, it's your own fault. If you go, let's have a look at the test. If you say continue here, then I'm sorry, but you're an idiot. Right now, that's possible. I think I'm going to make it impossible later. But right now, that's possible because we set this up here before we type check those statements. So according to those statements, we're within a for loop. But that's it, basically. I don't think there's anything else to check. It just needs to be within a for loop. And break is like exactly the same. Except we're saying break must be within a for loop. So this one is break. So I think that's what got our type checking sorted. So I mean, we can test that just by like saying, yeah, we've got highlighting, continue break like that. Those should throw type checking errors. So that's type checking done. Now generation. We're not doing GLSL generation for a lot of these new features. GLSL generation is very limited right now. You can't even call a procedure. You can't do a lot of stuff. But I'm going to expand the test suite so that basically all the tests get run on all the backends. So x86, GLSL, those are the only two backends in this case, but yeah. That reminds me, I feel like this is a real stretch goal, but we could put here. Yeah. Let's say stretch goals. Sort of like Android, iOS, web, you know, there's all these different ways that we could, platforms that we could support. So ARM and web would be like compile targets, and these are more platforms. So I've put Mac and Windows up here because I feel like they're sort of core platforms to support, but Android and iOS down here. Okay, just to add to that list. So where were we? That's right, we're in generation. So we're generating a statement now, and we want to add our new ones, continue and break. So generate, continue, generate, break. I'll just do the same old copy return business. So we also need to know more context here. And these continues are going to be like really simple. So we start, yeah, by just saying this is a continue. And then we're going to have the actual statement here, which is just, I mean, it's just jumping to a specific label. That's basically it. Yeah, so this is where we need the label. So this is where we need some extra context, like for index, basically. So I did used to have a for index, but then I generalized everything to label index. No usages. Yeah, it seems to have got a bit confused. So there's if, there's for, and that's right, there's vector assign. I thought so. So when we do assignment, using vector, which is like SIMD operations. We also have an index. So I think what I'm going to do is I'm going to add a for index also. But what we need to do, no, we've already confirmed that we're in a for loop in type checking. So I think now what we have to do is when we go into the for, we need to say context.for index equals for index. Like that. So we save it into the context. We don't make a copy of the context here, do we? No, this is what we're passing down to everything. So we make a copy of the for index so we know which for index we are in. And if we have nested fors, it'll be the most nested for will be the for index. But we need to, when we come back out, this is the tricky one. So I think we actually need to let's call it the initial for index. I can put it up here like that. And then we could even do that maybe. And anywhere where we used for index, we use the context one. Like so, but then right at the end, like this here will revert the stack index, and then this line here will revert the for index. So when we come back out of the for, then it goes back to the for index of the outer for, if we have nested for loops. So then if you, like we had nested for loops here, if you had to continue here, I mean that's pointless, but if you had that there after this for loop, it would make sure that it continues this outer for loop, because this for loop is finished and we revert the for loop, the for index to what it was before, which would be the outer for. Okay. Now, for a continue, this is where it gets tricky. We need to figure out, when we do a continue, we want to make sure that, like if I continue this for loop, it needs to jump to the bottom and do this. It needs to do that and then do the next iteration. And this here, I believe, is this here. Yeah, this is like the body of it, and this here is the extra thing. So I just need to add a new label above that. And I'm just going to call it a continue label, because that's the only reason for it. For index continue. So we want to jump to this. That's what the continue does. Yeah, jump to for whatever the index is, continue. We're using the context for index. I think that's it. And for end is how we exit the loop altogether. Normally it'll be because the condition failed, but in this case we want to jump to the end. And then it will just do a deallocation if it needs to, and then we're done. Okay. So we should be able to just copy this continue for a break. Generate break. And So for something end. I think that's it. It's just a jump. So I think that's continue and break done with tests, which I probably disabled yet. So let's do this so that we run the tests. Okay, forward zero end not defined. Let's go to test. Well, there's forward zero end. Oh, because it should be dot. I think it should be dot forward zero end. Let's go to the for jump. Yeah, see, it's jumping to dot something. Yeah, okay. So now that I added the dots there, I think they should work. This is more promising. And we should get an error saying that, was it break or continue? Continue. We should get an error saying that continue needs to be within a for loop. If all the tests pass and then it comes to the example. It's taking a while to run these tests. I'm sure it's not normally that long. It could be an infinite loop. That is a distinct possibility. Okay, let's go to our tests and let's just like disable all the other tests. So we have all these general tests. So get rid of those and these ones above. This one is a pain in the ass to comment out, so I'm just going to delete it. And down here, we're just going to say, I only care about general tests. So it should only run those two tests that we wanted to run, the new ones. And it's still taking ages. So I think we have an infinite loop. Let's take away the continue because I think that's the most likely to be an infinite loop. Yeah. So this one seems to have passed. And then we get continue must be within a for loop, which is great. Now we should get break must be within a for loop. Great. And now everything should work. But continue does not work. It is an infinite loop, but we should be able to see the assembly for it. So here's 40 continue, which gets R14, or gets whatever's on the top of the stack, adds it to something a bit higher in the stack, and then jumps to 0. So where's our allocations? Here's two allocations right at the start, 0 and 10. Yeah, that makes sense. 0 and 10. So it's adding that to that. I feel like that's not right, actually. Oh. Wow, yeah, that was legitimately an infinite loop, I think. Yeah, because it's never decrementing value, so it's never going to end. Okay, so it's actually an error in the test code. I think. Yeah, that's fine. That passed. Okay. Let's undo that. Undo that. Why is that all commented out now? Where is our, this is the, oh, we've got an error up here, but this is the only cable we've changed, so probably, that should be like that. Okay. So now we're running all the tests, which shouldn't take so long. There we go. Okay, so we're happy. We have continue and break. I mean, it wasn't that hard to implement, really. So what else can we tackle? Oh, I forgot to set a timer. Let's see, we are half an hour in. I'm just going to set a timer so I know how much we've got left. What else can we do? I just saw this here. This is like another kind of fairly fundamental feature, I guess, that we could add. Bitwise and an OR. So let's try that. I guess we need, well, we can go to the grammar again. It's another grammar change. So there are new binary operators. We have, this is, I guess, logical and an OR. I'm not sure what the best term is to use. But let's go to Odin. Forgot to close my email. Okay, I'll blur that out. I need to remember to blur that out. So if we go here and we go to like precedence, here we go. Here we go. So this is OR and then it's AND. Okay. So they're actually the same precedence as like some existing operators. I'm kind of surprised. So OR is the same as plus and minus. Okay. Plus minus OR. Okay. So if I go like that and like that, and now we have the extra operators. And then we go to, not parsing, tokenization. We need to add ampersand, and I guess it's pipe. Yeah, pipe. Pipe and ampersand. Okay, so now we have those extra tokens. And because they're in this map, they should get tokenized properly. We can move on to grammar. Actually, move on to grammar. That's totally wrong. Let's say to do, that's another thing that I thought of we could put in there. Okay, let's get rid of all this stuff. So we've done tokenization. So the next thing to do is type checking. No, the next thing is parsing. After tokenization, we do parsing. So this is parsing of right-hand side expression. This is where, oh, is binary operator. So we need to add it to the binary operators. ampersand and pipe. I think that there is also, while I'm remembering this, yeah, binary operators is in here as well. So that would be, what would these be called? We already have, these are not in alphabetical order. That's outrageous. This is outrageous. G, H, I, J, K, L. L, M, N. Okay. Add and equal L, M, N. Greater than this, then or equal, greater than or equal L, M, N. Subtract divide would go here. M modulo LMNO. Okay. All right. Whew, that was scary. So now I'll call it Bitwise. Bitwise and Bitwise OR. I need to add those. Okay, so we have the new operators. Cool, so binary operator is going to be happy. And I think toNode type is going to need these. This is another place that could do with some ordering. Element OP. Asterisk and backslash. Plus percent plus pipe goes in the middle there, and ampersand goes there. Okay, so single ampersand is bitwise and single pipe is bitwise. So that's how we map from our tokens to our node types, which we have it in there. And the last thing is our precedence. So I think we figured, let's have a look again, but there's bitwise OR, it should be the same as plus and minus. Bitwise OR. Oh no, these are token types, so that will be actually pipe. And I think it's asterisk backslash ampersand. Yeah. So this now will have ampersand. So those are 5. Well, we don't have the same number sequence because we don't have 1 and 2. but that should be right. So that should get the precedence of those operators correct. So I think that's parsing done. Now, type checking. I guess these could be like this also, right? Could have or equals and oh, these are percent signs. I think that's a bit of confusion. I think those should be ampersands. That's better. It's modular equals. So we should be able to go or equals and ampersand equals. I guess that would be there. We take this one out and we put equals on the end, and then we check to see if that actually looks right. Equals, or equals, and equals. Okay. So those are assignment operators also. Crap, so I need to add them as tokens. So it's like ampersand equals and pipe equals. So then we need to go to tokens and actually add them. And what were these lists again? Binary assignment operators. That's where we need them. Ampersand equals and pipe equals. Okay. So hopefully that's all we should need for parsing to work. And then in the AST, we will need, so what do I have? It's like multiply assign. Okay. So it's like bitwise and assign. Bitwise or assign. And do we have lists? We don't have a list of those. So where, for example, do I use modulo assign? We use it in here. That's in generation. Here's type checking. So numerical types can use basically all of them. Bitwise and bitwise or. Do they make sense with floats? I guess just to be simple, I will allow them with floats. If it's an array or a slice. I think we should not allow it for these, for floats. For floats, we should not allow. Okay. that's saying for floats, you know. If we're consistent, let's see, we'll put these single quotes. So then what's our other restrictions? Arrays of floats, cannot do those. If it's just a float, also it can't do it. Yeah, I'm going to say that it's only for integers right now. I don't know if it makes sense for floats to do a bitwise, but maybe it does. I don't know. But we're just going to leave it out for now. And atomic integer types can only do add a sign, subtract a sign. Okay. Cannot determine type. So this is all of the assignment restrictions, I think, sorted. So it's only for numerical types, not for arrays or slices of floats, and yeah, just not for floats, just numerical. Yeah, I think that's covered. Okay, so let's type check expressions. We should have something similar going on in here. Yeah, binary operator. Let's put this also in quotes. So how does this work? Probably something kind of similar, right? Numerical. If it's a bool, it can only be and or. If it's not numerical, or it's and or. Yeah, so it's either a bool of these or it's a numerical of not these. So now we've narrowed it down to bool or numerical. And bool, we've made sure it's the right ones. So floats, I think we're going to say we're going to give some options here. Wrong keyboard. So this is bitwise and bitwise or. So we're not allowed to do that with floats. And this only allows comparison operators for the atomics. Okay. I think that covers it. So it should be only non-atomic integers, just basic integers should be the only thing that we can do these operations with. I think we've restricted that now. So we can move on to generation, assignment. So it's not just an equals. And basically we've said it's for integers, so it's in here. So we can add to this list. So I'm not sure what order to put this in. You know how I like my ordering. But let's, because I think add and subtract is also or, bitwise or. So let's call this bitwise or, and then we'll put bitwise and at the end, I guess. And is it just the, I think it's just the OR operation. or an x86-64 NASM. Pretty sure, yeah, OR instruction. Very simple. Yeah, okay. So that's it. So easy. And then here we use the AND instruction. We might want to make sure that our right-hand side is in a register because this is likely going to be memory. So if we go to, here's AND. So we can have a register AND equals anything. Or we can have a memory AND equals just these things. So we can't have memory on the right-hand side if memory is on the left-hand side. That's pretty standard with the x86-64, it seems like. You can't have memory on both sides. So, especially because this is AND assign, the left-hand side is, basically it's always going to be memory. So we're making sure that the right-hand side is not memory. Interesting that we could have like copy to non-memory, which is basically copy to, no, yeah, we could have that so it would stay immediate if when immediate is okay. But let's just do this for now. So that was really easy. And I think expression is going to be just as easy. So we want a bitwise OR. So this is bitwise OR assign. And bitwise and assign. This is bitwise OR. So normally we do something like this. So, and now we're copying the left-hand side into a register so that whatever gets the result is does not affect the original. So this is OR, and then I should be able to just copy this down here and change the ORs to ANDs, just like that. And I think that should take care of OR and AND. In our value tests, or maybe it's numerical tests, we have modulo and modulo assign. Yeah, divide, assign. Okay, so let's go add, subtract, assign. So let's say bitwise OR and bitwise OR assign. So that's an interesting question, actually. What is the result? Of ORing var 0 and var 1. So if we go down here where we define them, this is the numerical tests as 2, 4, 6. So we're talking about 2 and 4 is value 0, value 1. So ORing 2 and 4, which I think, because in binary, if you have like 4, 5, 6, 7, 8, I believe 2 is like this, and 4 is like this. This is 0. So the result of this or this should be this. Anywhere where there's a 1 gets carried. And this should be 2 plus 4, basically. That should be 6. Let's bring this down here. And now we've got var 0, which was 2, or equals, let's say or equals or equals 2. So that results in a so I think we can actually do like this. Or equals 2 equals 2. So if var0 is 2, and we do or equals 2, then var0 should equal 2. Because we're oring with itself. Now if we do like or equals 4, we should get 0. And the reason is, so if we do 2 or 2, 2 or 2, we get 2. Because it's a 1 here or it's a 1 here. So 2 or equals 4, we're saying that or that, we get that. So that should actually be 6. So maybe we just do that. That's probably a better simple test. So then we've multiplied, divide. Let's put some bitwise AND tests. So go AND equals. So 2 and 4. Let's bring back our thing. We did get rid of it up here, didn't we? Yeah. So these are our, this is a 1 byte number here, 8 bits, 1 byte. So we have 2 or 4, no, 2 and 4. Whoa, no, I just want to press enter. So 2 and 4 is going to give us 0. And if we say 2 and 2, we should get 2. No, that's 4 and 4. 2 and 2. So if we go like that, then we should get, so the AND is saying it needs to be a 1 in both of these to carry through. That's AND. So AND it with itself, it should be just what it is. And these, since they have 1s in different places, results in 0. So 2 and equals 4. So let's do 2 tests here as well, like we did above. So now 2 and equals 2 should be 2. 2 and equals 4 should be 0. Let's try that. Fingers crossed it works. If I understood AND and OR correctly, and my maths was right. Ooh, unsupported node type. Somewhere we have not done things correctly. Okay. So we need to add pipe equals, bitwise or assign, and ampersand equals is bitwise and assign. Let's try that again. Binary upper bitwise OR is not valid for type atomic I8. That's correct. So I think we need to add it to in our tests. We have like these ways. I think I'd like to restructure this because this code is starting to get a bit messy. We have all these exceptions that we're putting in. Oh, and I realized something wrong with this. I think. No, maybe that's fine. Modular you just can't do with floats. Okay. So somehow where, here it is, atomics. So for atomic integer types, a non-atomic integer test. Okay, so we have like a whole list here because there's a lot of them. So here we have like or, oh, it's like a bitwise or, I think I called it. Bitwise or assign, multiply, divide, and this is the ands. Let's do the debug version. So if we get an error, hopefully we'll break when we want to. Bitwise and is not valid for a float. That's right, we also need to remove it from floats. I think I still have it in the it's float type and we're talking about bitwise or bitwise and. Yeah, so this gets a bit messy, you know, we just have like all these exceptions to these tests. Okay, so it should not happen for floats or atomic types. Should be only for integers. I think that's the only thing that's left. Be curious if it works for I8 because modulo didn't. Ah, this is where we got it wrong. And so this is the one, okay. Yeah, I put modulo here, but really, I think it's here. Because it's just U8 that it should be. Okay. Invalid token type equals. Okay. Bitwise and assign. All right, let's get back to that. But this here, I want to say like that. Anyway, I think multiply actually works for U8, but anyway, that should be enough. So invalid token type, bitwise and assign 5. So where's our bitwise and assign 1, 2, 3, 4, 5. It doesn't like and equals. It's finding and then let's go to our tokens, make sure we did the tokens right. No, it's not here, it's tokenization. Oh, I did mess it up. This one I got right, okay. Fingers crossed, come on. It feels like we've tried these tests many times to get it working. We're just over an hour now. Hey, everything's working very slowly. We do have a rogue window, but it's all working. We have bitwise or. So now like a real test for it actually is if I search for pipe in our bang code, there are some places where we've done this. So I kind of want to copy all that text, but if we say like this, and I just want to, hopefully I could just ask Grok for it. Codes for these Linux constants. Okay, yep. Those are the hex codes. Cool. So now in standard library core OS Linux, where to put it? I guess I'll put it right at the top. So prot read. I guess we'll call them i64s. Prot write. And these guys, put them in alphabetical order because that's how we like it. And then when we go back to memory here, for prot, we can actually do this. We need to do Linux dot, but that should work. I don't know if we actually use the heap allocator, do we? Yeah, we're not actually using it right now. But that should work, and we can, there's another place we can test. If I search for the pipe again, so that's all good. Yeah, and threading. This is another place where we use it. So did I close memory? Basically want to do the same thing here. And threading. Now I have to be careful here because I'm going to delete these two variables, which means there's two less variables here to account for. Let's try that. I'm quite nervous. Core dump, okay. That's not great. And that could be because I messed this up now. There's two i64s that we're not declaring anymore. So that should be that. But maybe I can just go strings.println strings.i2a, put that in there, go buff, and buff is what, some big i8 buffer, and we need to import strings and see what happens. I think we need to actually maybe turn off the tests for now. Okay, so we get a big number, which I think is wrong. Yeah, these prots all together should just be 3. Prot read, prot write. So I think that OR is not actually working. And if I go back to the Linux file, yes, we have OX1, OX2. I mean, they are signed. Do you think that's the issue? No, but I don't think, you know, the OR and the AND, it's not going to care whether I call it signed or not. The operation is still the same. We don't do any conversions or anything. So for some reason, it's deciding that's a massive number. This is Bitwise OR apparently. And these are on 64-bit numbers. So that or that equals that. That makes sense? OX1 or OX2 should be OX3. But we're getting a big number. We are treating it like a signed, we're doing signed division. Maybe that is an issue. So if I do that, and then just to make things simple, where was it? Was it in memory? No, in threading, I think. We'll do an I to a U, just so I don't mess with any other code. So I to a U takes a U64. Let's try that, see what happens. U and I64 are not compatible. Memory, so let's just revert this for now. And in threading, okay, so we just have this thing that shouldn't actually affect anything else. Should run properly. Cannot negate type U64. So I guess I to a U does not need this part. Okay, so we get a big number still. Why does it print out twice? I guess it might be starting multiple threads before it crashes. Well, that sucks. But wait a minute, why is it crashing now? Everything is as it was. Okay. Wow, so these lines actually cause it to, because now we're messing with the stick. This whole procedure is crazy. So why does that OR give us a big number? What does AND give us? Also another big number. So now that we have OR, let's search for OR. Oh, just in this file. It's like ORing with itself. I don't know where this is. This is start thread. This is calling the print line. and iterate u. So that's that line. And then the line before, this is nil assigning something. That's the buffer. This is doing the OR, so it's allocating some space. But look at this, these are both RSP plus 116. So it's actually, it's looking at stack addresses. Oh, wait a minute. That's interesting. Okay, because we're importing these things. They are on the stack. I haven't done it like this before. These two are actually on the stack. Because if we go to the Linux file, they're just stack variables. But it's not grabbing them correctly. But it should actually work. I feel like it should work, but maybe it'll work better now that it's, yeah, there we go. Now it's saying 3. So it was messing up the addresses. Now that it's using static variables, it works. Okay. So bug stack variable import uses wrong address. Yeah, there's something wrong there. But once we make it static, it looks good. So now I think we can put this like this. That takes away one variable. We'll just try that. Because I64 versus U64, but probably we don't need to make these U's anymore. It still crashes. What does that say? It says 3. Okay. I feel like that should work. Maybe like that. So the only thing we've changed is this. Okay, that worked. Okay. If I do Linux dot there, that still works. So if we cut these two variables out, I feel like we should be able to reduce that by 2 and it should still work. Yes. Okay. So these also, I mean, really I should be able to do just a call to, I should be able to just do like a heap allocation here, but our allocator stuff is a bit weird, so let's not play with fire. And we'll just put this here. So actually that can just be a one-liner. Okay, so now if I search for the pipe in Bangalang code, so it's just these thread ones left. This is Bitwise OR, so if I go to our hex codes, so we're at nearly an hour 20. I think all I want to do is just sort out these hex codes. So we can do those ORs and then we're done. So fingers crossed this does not like cause a whole lot of trouble, which is, I'm not gonna lie, it's on the cards. It might screw everything up. So we should be able to do this. Boom, 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 boom. Assuming that Grok got it right. Then we should be able to put these in here and just say a Linux dot That should work. Cool. That works. So we should be able to take this variable out, which means we can reduce that by 1. Oh my God, really? Really? So if I go like that, it works. What the hell? I guess here, do we do a stack allocation or something? Maybe we do. Let's go to start thread. We do an allocation. Interesting, we do an allocation, we don't do a deallocation. Because it's for the response. Yeah, so we just put the first one into a register, and then we OR it with a bunch of others, and then we move it into that register so that it's in the parameter to the syscall. So we don't do any allocations. I'm worried about allocations because this procedure here is really crazy. We're creating stack memory, and then we're massaging it so that the child process, when it continues from here after the syscall, the child process will continue from this exact point. Its stack should be such that it can use the parameters to this procedure, and it can use PID, and everything's fine. And part of that is accounting for all the local variables that have been declared. This is one of them. So if I take that away, I feel like that should work. But it doesn't. So what if I just still say that it's 5? See, I find that really crazy. I don't know why that would be. That doesn't make any sense to me. But it works. So let's leave it. I mean, there's like 1, 2, 3, 4 variables. But I'm accounting for 5. Okay. Madness, but whatever. It works. And we have bitwise or, bitwise and. And they were working. Why was that? Yeah, there was the address thing that was causing issues before. Crazy. Okay. Yeah, I think we got a bit done there, right? We got bitwise and an OR. And we got break and continue. And that's a pretty good session, I think. It did go a little bit long. But thanks for stopping by. Have a good one. Ciao for now.